Hello everyone, my name is Daksh. Here I am representing my team YHD. Today I would like to talk about our course project titled Wireless Smart Hub using Verilog HDL. So let's get started. So let's have a look at the problem statement. We need to design a hub that can handle and route data for 3 devices. The hub has the ability to store data to which devices can access quickly. But what if the memory is full or data is not found in the hub? It has no way but to access data via satellite. So we need to maintain a practical balance between latency, communication cost and unit cost. So this is the approach that we followed. Based on the resources available, we designed our memory architecture. Our main focus was to have least evictions possible to reduce communication cost and latency. We considered all the possible cases and based on that we designed a state diagram. Later, based on the state diagram, we implemented our code and tested all the 3 traffic files. Based on the results obtained, we calculated the communication cost, unit cost and the latency. So here is the image representing the memory architecture of a smart hub. We are using M1 memory to store and check tag addresses of the data stored in all other memory locations. We are using M3 for storing data for 512B, M2 to store the data for 128 bytes, whereas 8M3 to store the data for 1024 bytes. We will see all of them individually in detail. Here is the brief idea about how we are storing 128 bytes of data. We are using 4 M2 memories, each of 32 byte width and having 16 locations. We are using an address pointer that points to the same location in all the 4 modules, so we get the data out sequentially. So now you will wonder, how are we doing address mapping? See, we have 32-bit tag address and only 16 locations. So what we do is we store the X and the X plus 16 address data in the same location. So the first and the 17th address will be stored at the same location, second and the 18th address will be stored at the same location, and so on. For the 512 byte data, we are using a single M3 memory. It is 512 bytes width and it has 2 columns. So all the odd addresses will be stored here and the even addresses will be stored here. For 1024 bytes of data, we are using 8 M3 memories which are 128 bytes width and has 8 lines. So we can store 8 of 1024 bytes of data. The mapping is done such that the first and the 9th location is stored here, the second and the 10th location is stored here, and so on. We are using victim memory in our project. It basically follows the concept of victim cache. It is virtually located between the M2 memory and the satellite. So whenever a miss occurs, in the case of write, you can write the data into the victim cache, or for the read, you can read the data from victim cache. So basically it prevents you from having an eviction. In our project, we saved 7 evictions which approximately profited us this many cycles, and it just cost us $3. In this project, we are using the concept of victim memory only for 128 bytes of data, and we are using M3 memory. So the width is 128 bytes and it has 8 locations. This is the basic block diagram of our project. The clock and the reset are the basic signals. So the device sends a command through this pin and the data is sent through the data in pin to the smart hub. Now whenever a device requests a data, so the data is given out from the hub to the device from the data out pin. The transaction request is the pin when the device sends a transaction request to the smart hub for sending or receiving a data. Link busy is a signal which indicates that a transaction is going on between one of the device and the smart hub. The output signals are T satellite, which indicates that the smart hub is sending a data to the satellite, and R sat indicates that the data is received from the satellite to the smart hub. The data satellite indicator indicates that some transaction is going on between the smart hub and the satellite. This is the algorithm that we are following in our system. First of all, a request is given by the device. So we first check that are there any other requests going on. If there, then the device has to wait. Then we check whether it is a read operation or a write operation. If it's a read operation, we check the tag address and the valid bit. If it's a hit, then the data is read from the memory and it is given to the device and it's the end of the operation. But what if it's a miss? Then the data is taken from the satellite. Similarly, for the write case, we check the tag address. If they match, then we write the data to the memory location and display the time required for that operation. But if it's a miss, then again there are 2 conditions, a valid and a dirty bit. So if the valid bit or the dirty bit is 1, the memory contains the data of different locations. So we need to evict that data and replace it with the new data. but if the valid bit and the dirty bit is 0, it means that the location is empty. So we can write the data directly into the memory location. This is the algorithm that we used for our victim memory. So we are using victim memory for 128 bytes of data. So now for victim cache there can be a read operation or a write operation. Let's consider each of them individually. So for first read, we check if the tag address of the map memory location matches with the tag address. So there can be a hit or a miss. If it's a hit, we read the data directly from that map location. But what if there's a miss? So we have no choice and to access data from the satellite. And now for write, again we check the same tag address of the map memory location with the tag address provided. So there can be a hit or a miss. So there can be a hit or a miss. So if it's a hit, then the tag address matches in the victim cache. Now depending on the valid bit and dirty bit, either we evict the data or we write the new data directly to the victim cache. But now what if there's a miss? If it doesn't match, we write the data to the map address in memory location, checking its dirty and the valid bit. If the valid bit and dirty bit both are 1, we transfer the data into M2 memory to victim cache and evict the data from victim cache. But if any of the bit is not 1, we simply overwrite the data in M2 cache. So this is the state diagram that we designed for a smart hub. The first state is the initial state. If the reset is 1 or if there is no trans request, then we are in the initial state. If whenever a device gives a transaction request, we then go into the command accept state where the command is accepted. Now the next state is the checking state where main thing happens. So now we check whether it's a read hit, write hit or a miss. This all happens in the checking state. If the TXRX bit is low, which indicates that it's a read operation, and if the tag address matches, it's a read hit. So the data is given to the device and then it's a read hit and again it goes to the initial state. Now consider for write hit. So now the TXRX bit is 1, which indicates that the device wants to write the data into the memory. So if the tag address matches, it's a write hit, and once the write hit is done, again it goes to the initial state. Now what if there's a miss? So for miss, it can be either read miss or write miss. So if the TXRX bit is 1, which indicates it's a write miss since the tag addresses are not matching. But if the TXRX bit is 0 and tag addresses are not matching, it goes into the read miss state. So after the operation is completed, if it's a write miss, then the write miss signal goes high. If it's a read miss, then read miss signal and RX signal goes high. And again we go to the initial block. So now the second device can give the command and the same procedure is continued. So we carry on this state diagram as we go on further. Now let's have a look at the simulation results. I will go through each of them individually. So first is a read hit. So now whenever a transaction request is given, as you can see high over here, it goes on to the next state, that is the command request state. And after command request state, it goes to the checking state where all the main operation happens. Since it is a read hit, the read hit signal goes high, as you can see. The device ID is also shown over here along with the tag address of the same. Now since it is a hit, so there is no victim access and the RX signal is also going low because there is no transaction going on between the satellite and the device. This is the condition for write hit. So again, as you can see, there is a transaction request over here. The device ID is shown, and since it is a write hit, so the write hit signal goes high over here and the tag address are shown as follows. And since again there is no transaction going on between the satellite and device, this signal is low and the victim access is also low since it is a write hit. So we are also displaying all the operations, how it goes on and the time it takes. So we will see the delay calculation in the further slides. So now let's consider a case of write miss. So for 128 of bytes of data, we have a victim memory also. So now let's have a condition when there is a write miss for 128 bytes, but there is a write hit for the victim. So now the transaction request is given, and then as you see the device ID is 01 for 128 bytes of data. It's a write miss. So and also you can see that it's a victim access since it is a write hit, and you write the data over there. So here you can see that the request from device 01 is coming. The write operation takes place on the victim cache in 1472 cycles. So this is the delay calculation that we will be showing in further slides that it takes. So now let's consider a case of write miss but the dirty bit is 0. So here again the transaction request is given, the device ID that you can see, since it's a write miss, so this signal is high and the tag address is given below. But now as the dirty bit is 0, you can directly write it to the data, so there is no eviction. So here you can see the request from device 1. While the operation of tag comparison takes place, the command and the data will be received. So since dirty bit is 0, there is no eviction. So here you can see the result of dirty bit 0 and no eviction taking place.
Thank you, Daksh, for this explanation. Now my name is Yash and I will continue further. So basically for this project we are having 3 benchmarks based on which we would be judged. So these are the latency calculations, unit cost calculation and the communication cost. Now one by one I would like to explain each of them. So let us start with latency calculation for 128 bytes. Okay, so let's start with the hit. When the hit happens, we basically would be following this sequence. That is, initially command would be sent to the buffer. After that the command is being accepted by the 128 bytes of M1 memory. It would compare the tag addresses. After comparing the tag addresses, it would determine that a hit has occurred. After hit has occurred, it would finally accept the data from the device that is sending it or transmitting it, and later it would be stored in the buffer of 16-bit each. Because the data bus is of 16-bit each, we need to store it 16 by 16 bits. Okay, so after that the last part would be transferring the data from buffer to our memory, that is 128 M2 memory for 128 bytes. Okay, so I would like to explain how exactly do we reach to this number or the clock cycles, and the others would then become self-explanatory. Suppose following the sequence that I explained before, it would take 288 clock cycles to accept the command from the device which is transmitting it. After that it would take a single clock cycle to compare it with the tag, to compare the tag address that which are transmitted by the device. Now that the hit has occurred, our smart hub would transmit a signal stating that it is ready to accept the data. Now it would take 18432 cycles to accept the data as it is of 128 bytes, and later it would take 512 clock cycles to transfer the data from buffer to memory. Thus if we sum all of them, then it would take 19234 cycles for a hit request. Similarly, the same can be calculated for the other cases as well. The calculation for each case can be found in the document. Here are the latency calculations for 512 and 1024 bytes, which can be done in the same manner.
Now let's have a look at the communication cost calculation. Since it is given that $1 is cost for 1 minute, so it will cost $1 for 60 into 10 raised to 9 nanosecond. It's a simple math. So now it is given that one cycle is 10 nanoseconds. So if we convert 60 to 6, it will become 6 into 10 raised to 9 cycles for just $1. So now since the command is 32-bit wide, it takes 2656000 cycles to send. So it will cost $0.0004. So similarly for 128 bytes it costs this much, for 512 and for 1024 it costs this much. It is given that M1 costs $50, M2 costs $10 and M3 costs $3. So we are using 1 M1, 4 M2s and 10 M3s. So the total cost is $120. So our unit cost for the smart hub is $120. So finally, conclusion. We have successfully implemented the smart hub in Verilog HDL. Victim cache is the highlight of our project because we were able to save like millions of cycles because of the concept of the victim cache. The smart hub has the facility to store data for all the 3 data sizes, that saves millions of clock cycles required to receive data from the data center. I hope you liked the video and you understood our project. Thank you so much.